My dear students, in this video, I am going to start the 7th chapter in the 12th standard mathematics state board syllabus. In this volume 2, 12th standard mathematics state board syllabus in volume 2, I am going to start the 7th chapter. The topic is applications of differential calculus. Chapter 7, volume 2, state board 12th mathematics. 7th chapter, applications of differential calculus. Differential calculus. Seventh chapter. This chapter mainly deals about the applications of differentiation. That is, the primary objective of differential calculus is to partition something into smaller parts. So, introduction. The primary objective of differential calculus is to partition some elements into smaller parts, that means infinitesimal parts, so that in this topic differential calculus in earlier days it is called as infinitesimal calculus. That's why it is called infinitesimal calculus, because it split the particles into smaller parts. Some mathematicians like Riemann, Newton, Hein, Leibniz and Euler, these mathematicians are very much dealt about this differential calculus, applications of differential calculus in their fields. For that, differential calculus as application in geometry and dynamics. These applications of differential calculus is mainly used in the topics geometry and dynamics, derivatives of functions representing cost, strength, materials in process, profit, etc. are used to determine the monotonicity of functions and thereby to determine the extreme values of the quantities represented by those functions. See, in the area like cost, strength, materials, profit, in these areas, especially in physics and astronomy also, this topic is mainly used to determine the quantities. Derivatives of a function do find a prominent place in many of the modeling problems in engineering and sciences. Differential calculus has application in social science and medical science also. So these applications of differential calculus is used in medicine lines also, engineering and science. So approximation and everything is used in this topic. Now we will see the first unit in this topic, application of differential calculus. Derivative, meaning of derivative, that is derivative as slope. Our first idea is derivative as slope. Derivative has slope. Slope or gradient of a curve. Slope or gradient. Slope or gradient of a curve. Suppose y equal to f of x is a curve. Y equal to f of x is a given curve. And this curve, a point x comma y point P x comma y is a point on the curve. P, this is the curve y equal to f of x. If you draw a tangent at a point P x comma y to the curve, so y equal to f of x is a curve, given curve, P x comma y is a point on the curve. This is y-axis and this is the x-axis to the curve. This is angle theta, angle made by the curve with the x-axis. Origin. This is origin. This is the angle made by the curve theta. This is your x-axis and this is the y-axis of the curve, y-axis of the coordinate axis. Origin. Theta is angle made by the tangent to the curve with the x-axis. The measure of the angle in the anti-clockwise direction from the x-axis is theta. P x comma y is a point on the curve. Now the gradient slope of the curve y equal to f of x is a given curve and P x comma y is a point on it. Now if you draw a tangent at the point P to the curve, it means it makes an angle theta with the positive direction of x-axis. Okay. Now the slope of the line joining two distinct points. There are two distinct points on the curve P x comma y. Suppose it's a point Q. It is x plus h and y. Y is f of x plus h. X plus h and f of x plus h is another. Y equal to f of x. This point P x comma y is otherwise called x comma f of x. The P is also called x comma y. Y is equal to f of x, we can say. Therefore, the point P x comma y we can express as x comma f of x. So the slope of the line joining the 2 points P comma Q, where x comma f of x is the point P and Q x plus h comma f of x plus h is a point Q, where h is the small increment in x. Small increment in x and y. X is a small increment. Now, the slope of the line joining the two distinct points, the slope of the line joining two distinct points, x comma f of x and x plus h comma f of x plus h. The slope of the line joining the two distinct points x comma f of x and x comma f plus h comma f of x plus h is defined by f of x plus h minus f of x divided by h. This is the slope, Newton's point. Slope of the point, the slope of the line joining the 2 points x comma f of x and f of x plus h comma f of x is f of x plus h minus f of x divided by h. This ratio is called Newton quotient. This is called Newton's quotient. Newton quotient. This quotient is called a Newton quotient, and this is the slope of the line joining the 2 points. Suppose taking the limit as h tends to 0, we get, if we are taking the limit as h tends to 0. Now, after defining this slope, taking limit as h tends to 0, taking limit as h tends to 0, we get a limit h tends to 0 f of x plus h minus f of x divided by h is called derivative of f with respect to x, f dash of x. This is called f dash of x, limit of Newton quotient. This is called a limit of Newton quotient. This is a limit of Newton quotient. This is called a limit of Newton quotient, and this is called the derivative of f of x, and also it is called dy by dx. So this limit h tends to 0, f of x plus h minus f of x divided by f of x divided by h is f dash of x, and it is otherwise called dy by dx is equal to f dash of x is equal to limit h tends to 0 f of x plus h minus f of x divided by h. This is the definition of the derivative of f with respect to x, and this is also called the slope of the curve. See, which is the slope of the curve at the point. This is the slope of the point joining the 2 points. But this is the slope of the curve at the point x comma y, p x comma y. This is which is the slope of the curve. Slope of the curve h p x comma y. Slope of the curve h p x comma y or x comma f of x. X comma y is otherwise called x comma f of x. So slope of the curve at the point p x comma f of x is dy by dx, which is otherwise called f dash of x, is limit h tends to 0 f of x plus h minus f of x divided by h. This Newton's limit of Newton quotient is called the slope of the curve at the point p, and Newton quotient is called the slope of the line joining the 2 points x comma f of x and x plus h comma f of x. This is the difference. What is Newton quotient and limit of Newton quotient? Newton quotient is nothing but the slope of the line joining these 2 points. This is called f of x plus h minus f of x divided by h. This is Newton quotient. The limit of Newton quotient as h tends to 0 limit x tends to 0, f of x plus h minus f of x divided by h is called limit of Newton's quotient. This is the slope of the curve at the point P x comma f of x. That's all about the definition of the slope of the curve. And theta is the angle made by the tangent to the curve with the x-axis. Therefore, slope is dy by dx is also defined as tan theta. Suppose theta is the angle made by the tangent. Suppose theta is the angle made by the tangent with the x-axis. Then slope of the tangent is this, and the slope of the tangent dy by dx is tan value of the tangent, tan theta. So it's also the definition for the slope dy by dx is tan value of the angle made by the tangent with the x-axis is slope. So this is the definition of the tangent at the point P x comma y. It made an angle theta with the positive direction of x-axis. Therefore, tan theta is also called the slope, and therefore dy by dx is tan theta. Okay, the next, derivative as rate of change. Next definition we are going to see derivative as rate of change. Next definition. So first I have derived what is slope of a point, slope of the curve at the point. Slope of the curve at a given point is dy by dx. It is in the limit of Newton's quotient, that is limit h tends to 0. F of x plus h minus f of x divided by h is the slope, and it is otherwise called tan theta, where theta is the angle made by the tangent with the x-axis. Okay. So, next definition is derivative as rate of change. Derivative as rate of change. Derivative as rate of change. Suppose the function s of t gives the position of an object relative to the origin as a function of time t. Suppose the function s of t that gives the position of a s of t function of in terms of t. Suppose the function s of t gives the position of an object related to the origin. Position s of t, the function s of t is the position of an object, the function s of t is the position of an object related to the origin, The function s of t is the position of an object related to the origin as a function of time t. As a function of time t. S of t is the position of an object related to the origin as a function of time t. Then velocity of the function, velocity of the particle is, then the velocity of s at time t is ds by dt. derivative of the function s with respect to t. Differentiate the distance s with respect to t. ds by dt is the velocity of the particle at time t, and acceleration is d square s by dt square or dv by dt, because this velocity is defined by function of t, velocity v of t. S of t is the distance traveled by the particle, velocity of t, v of t is the derivative of s with respect to t, that is the velocity. Acceleration is derivative of velocity dv by dt. This is called acceleration of t. Acceleration at time t is nothing but derivative of velocity with respect to t, or double derivative of s with respect to t, d square by dt square. This is the velocity of the particle and this is the acceleration of the particle. Derivative of the time distance is velocity, derivative of the velocity is acceleration, that's all. Derivative of s, distance, derivative of the speed or distance, derivative of s is velocity. Derivative of velocity is acceleration. So ds by dt is velocity, dv by dt is acceleration, or double derivative of s, d square s by dt square is acceleration. Now we will see some remarks on this velocity and acceleration. The average rate of change, average velocity remarks the average velocity in an interval a comma b. The average velocity in interval a comma b is f of b minus f of a by b minus a. This is the average velocity of f of x is f of b minus f of a by b minus a is the average velocity. The instantaneous velocity is rate of change of the next one. The instantaneous velocity is ds by dt. Instantaneous velocity is ds by dt or f dash of x, derivative of x with respect to x. In instantaneous velocity, this is average velocity, and velocity is otherwise called speed. Next, the third one is speed is the absolute value of velocity. Speed is the absolute. Speed is the absolute value of velocity. Absolute value of velocity regardless of direction, and hence speed is the absolute value of velocity regardless of direction. Speed is the absolute velocity, absolute value of velocity regardless of direction. Hence, speed. Hence, speed is equal to absolute value of velocity. That is equal to mod of ds by dt. That is absolute value of ds by dt. This is the absolute value of velocity regardless of direction. Next one. When the particle is at rest, velocity is 0. When the particle is at rest, then velocity is 0. V of t. When the particle is at rest, velocity is 0. And next one, when the particle is moving forward, when the particle is moving forward, then velocity is positive. Greater than 0. When the particle is moving backward, then velocity is negative, less than 0. When the particle is moving forward, velocity is positive. When the particle is moving backward, velocity is 0. When the particle is at rest, velocity is 0. When the particle changes direction, velocity is negative, changes its sign. And one more thing, when the particle changes direction, velocity changes its sign. Velocity changes its sign. When the particle changes its direction, velocity changes its sign. These are the important remarks for the velocity, idea of velocity. And that's all about the introduction about the topic, applications of differential calculus. And we will solve problems in this topic in the next video. Thank you.